Hello, welcome back. This is Calculus by Dr. Oz. Today we're going to go over an exercise where we have two infinite series and we're going to show the divergence of these infinite series by using the test called nth term test. And this test is only designated for series which diverge. Okay, so we can't use this test for proving the convergence of the infinite series. And this is the very first exercise of this section. So let's practice the nth term test and let's hit the road.
All right, let's get started. Let's start with part A, and I want you to remember the nth term test. So let's check this out first. Nth term test says that if an infinite series converges, then the nth term must approach zero. So another way to interpret that, if the nth term does not approach zero, that means that the infinite series diverges. This is like a contrapositive. So not this should imply not this. Not this means that limit of an is not zero, then that implies that the infinite series diverges. So we're going to sort of like utilize this argument for two of those series. Okay, so all right, so what is an for this problem? An is n over 2n plus 3. Okay, so I'm going to just take the limit of an as n approaches infinity. Okay, so this is sort of like back to calculus 1. There are alternate ways to handle this problem. So one easy way is that the top is a polynomial of order 1, and the bottom is a polynomial of order 1 as well. So then the limit is in fact the ratio of the coefficients of the highest order term. So in the top, highest order term is n, so the coefficient of that is 1. And in the bottom, the highest order term is 2n plus 3, so 2n in fact, right? So the coefficient of that is 2, so the limit is in fact 1/2. Okay, another way to handle is, which is more rigorous, that you just factor out the highest order term from the top and the bottom. So, well, there's only one term in the numerator, so I don't need to factor that out. But in the bottom, the highest order term is 2n, so I factor that out. So I'm left over with 1 plus 3 over 2n. So this allows me to get rid of the infinity over infinity type indeterminacy here. So because here originally I have infinity over infinity. Okay, so this is sort of like one of the ways to handle infinity over infinity by factoring out the highest order term from the top and the bottom. So n's are going to cancel. So I'm going to be left with 1 at the top, and that means I have 1 over 2 times 1 plus 3 over 2n. So this way I can pass the limit, and if I do that, this term is going to approach 0. Right, because 3 over a large number will approach 0. So that is going to take this limit value to be 1 over 2. Okay, so there are two different ways to handle this limit. The first way that I used here is just a property that we learned in Calc 1. If you don't remember that, that's fine. So just factor out the highest order term and then do the simplification and pass the limit. Okay, so the nth term test says what? It says that if the limit is not equal to 0, okay, which is the case right here, because 1/2 is not equal to 0, okay? So this essentially means that the infinite series diverges. So I can go back and conclude that this series diverges, okay? And by what? By using the nth term test. Okay, this is a very convenient way of showing the divergence of infinite series, because in practice what we do is checking the limit. If the limit is not 0, then boom, you're done. The infinite series diverges. All right, for part B, we're going to apply the same strategy. I have a n, the n term, to be n plus 1 factorial and 5 times n factorial. Just in case if you don't remember what factorial means, let me just write here n factorial. It's essentially you're multiplying the numbers starting from n all the way to 1. So for example, 3 factorial is 3 times 2 times 1. Okay? And 6 factorial is 6 times 5 times 4 times 3 times 2 times 1. Okay? So we're going to use the definition of the factorial maybe to put this in the simpler form, because if I just pass the limit right away, well, the top is infinity, right? Because if n is infinity, infinity factorial is multiplying all of those numbers starting from infinity all the way to 1. That's just a huge number. So this is also infinity. So you're having infinity over infinity type indeterminate form. So to handle that, we simplify the top and the bottom by using the definition of the factorial. So since n plus 1, we have n plus 1 factorial and n factorial. So n is the number after n plus 1 in the description of n plus 1 factorial. So in other words, let me just write what n plus 1 factorial is. So I start with n plus 1, and then the next integer that I go with is just n, and then n minus 1, and going all the way to 1. So as you see that the relationship between this one and this one and this one is that, let me just write at the top here, n plus 1 factorial has one more factor, but the rest is exactly equal to n factorial. So it's n plus 1 times n factorial. Okay, so I'm going to use this right here. So it's n plus 1 times n factorial, and this is 5 times n factorial, right? So now I can cancel out n factorial, and now I'm left with n plus 1 over 5. And now I can pass the limit, because now I have a simpler form to work with. And the top, as you see, goes to infinity, and bottom is just constant, going to 5. And infinity divided by a finite number is going to take you all the way to infinity. So in other words, what we call this type of limits to be doesn't exist. Or you can, if you want to quantify that, this is plus infinity, okay? Which is definitely not equal to 0, okay? So this allows me to use the n-term test, because if the limit is not equal to 0, then the infinite series diverges. So going back to here, I can perfectly conclude that this series diverges by the n-term test. All right, so what I'm going to show you is how we can visualize the divergence. What I did here is for the first infinite series, I made a table here where I have capital N in this column. So as you see, it's increasing all the way, and I have the corresponding partial sum. So partial sum means that if you have Sn, it essentially means that you have, if this is the n term of the series, it's A1 plus A2, dot, 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 all the way to An. So when I say, let's say S5, all I'm doing is taking the sum of the first 5 terms in the sum, okay? So as you see that when n increases, the corresponding values are increasing linearly, as you see, right? When you go in this direction, or backwards in this case, so let's just wait for it to loop back forward. So we start from here, look at the partial sums, it's like 1.5 for the given values, right? And it increases without a bound. So if you probably put more terms, like I put first, I made n all the way from 1 to 100, as you see that it goes up to 40, but it keeps increasing when you add more terms in the sum. So this is the example of the first infinite series that it diverges, and for the second one, it's the same deal. This time I have n going all the way from 1 to, let's see, 100. We'll see that I'm going in this direction. And the corresponding values are increasing exponentially, as you see. Okay, so this is the first 100, so the highest value is here as 100, but if you increase this 100 to 1,000, for example, so the graph will keep going exponentially, growing. Okay, so as you see how it grows depending on how many terms you put in the partial sum. So the pattern is exponential. All right. All right, this is the end of the video. Thanks for watching. I'll see you in another video.